Introducing the A2PBEER Support Guide Toolkit. As part of the project, an online support guide toolkit has been designed and developed to assist building owners and managers in choosing the most appropriate retrofitting strategy. In this presentation, we will outline the methodology we developed for public building and district characterization and the systematic public building and district retrofitting. Then we'll guide you through the A2PBEER Support Guide Toolkit step by step. Finally, you can try yourself, and we would like to hear your feedback and your questions. The toolkit is to assist stakeholders in making best practice decisions on how to improve the energy performance of their public building or district. The guide outlines the methodology of how to carry out a district and building assessment from the viewpoint of energy consumption. A2PBEER adopted a holistic approach to retrofitting the buildings, considering not only the building requirements, but also the occupants and community requirements, all the sectors in the energy value chain. All building owners and managers should have an understanding of how the building works and how to improve its efficiency, improve energy savings, reduce CO2 levels, provide comfort for its occupants, and simplify its use. For the project, it was important to clarify the definition of a public building or district. Public buildings are defined as buildings that are owned or occupied by public authorities or are intended for the use of the general public. A public district can be explained as an area of a country or town that is fully or partially set up of public buildings. Also, the main aspects for public building and district characterization was researched. An important determinant of building energy consumption is the function of the building. Energy demand varies deeply on the building type. For example, space heating is the predominant issue in residential buildings, while not in offices, administrative buildings, where cooling and lighting would be the main type. The construction type, namely the wall and window type, and building geometry are fundamental characteristics that influence the shape and size of the building and in turn are equally important factors in energy consumption. Morphology and density can affect the size of the building envelope exposed to outside environment as an important determinant of heating energy demand. It also influences the availability of daylight and sunlight, which affects the energy consumption for artificial lighting and natural ventilation. The age of the building also represents a key aspect, as well as the energy systems, particularly the type, efficiency and controllability of the lighting, heating, cooling, and domestic hot water systems. All the above parameters determine the overall energy use and the best possible refurbishment methodologies of a public building. Based on the research on the aspects of the energy efficiency of buildings and districts, we found that there is a consensus for these main aspects for the characterization. However, there is no general rule on the definition of district boundaries. We defined two distinct types. Closed districts consist of large land extensions owned by the same public body. Generally, the borders can be clearly drawn. It is separated from its surroundings by a physical or functional barrier. The majority of the buildings are usually on the same type, with some distinctions. Typical examples would be university campuses or hospitals. In an open district, barriers are not defined by physical perimeters, but by usage and ownership. Main characteristics embedded in an urban frame and more stakeholders are involved in the decision-making process. Usually, they have a shortage of open spaces and shared utility network systems with other users. Examples include cultural districts and government centers. We also summarize the public district types based on function, as shown on the slide. Four types of district morphologies were identified, representing the main types of how a public building or group of buildings relate to their environment: the introverted, the campus, the mixed, and the embedded. While the introverted is completely separated, the embedded is a type where public buildings are blended into the city completely. The energy demand of districts is influenced by many other factors: the density, the intensity of land use, building heights, street characteristics, and connectivity were found to be the most influential factors affecting district energy demand as indicators of district morphology. The energy use of districts also consists of the energy consumption of the building stock, so usage patterns are factors to be identified: diversity, residential area rate, public building, non-residential areas in the area, industrial buildings in the area. Besides the buildings and morphology, district energy demand also includes the energy use of urban infrastructures, like street lighting, electricity supply, development degree of transportation, off-site renewable energy, district heating and cooling, and wastewater and water management. In the support tool, this transportation-related energy demand were decided not to be included, as it is mainly determined by other factors like type of public transportation, number of passengers, peak hour traveling, and so on, which are not directly related to the subject of this project. Climate is an important environmental factor. It is necessary to classify locations according to the predominant climate to know the means of energy consumption, which can be taken into account in energy-efficient building refurbishment design. Local climate at a specific district or building site can dictate what passive design strategies are most suitable and effective for that particular location. For example, strategies that are perfect for a hot, dry area may be counterproductive in a cold, humid climate. A site climate is determined by its latitude, altitude, and terrain. The A2PBEER climate classification takes into consideration the heating degree days, cooling degree days, average temperature, and relative humidity for the different zones. When the building requires a retrofitting strategy, the A2PBEER Support Guide Toolkit is designed to provide basic advice in a simple way. The flowchart demonstrates the methodology of the toolkit with the steps of the web tool. The methodology can be applied to all public retrofitting projects and used as a general energy assessment of a given site. Let's go through the steps and themes of the process. The first step, described in the developed A2PBEER retrofitting methodology, is to outline the key concepts of building and district assessment from an energy consumption point of view. It provides the characteristics with the most significant influence on the energy consumption of the public building, which determines the key performance indicators. The indicators are then compared with benchmark values depending on the climate to identify the relevant technical retrofitting gaps. These determine the technical intervention possibilities feasible for the retrofit. This slide presents a summary of the characteristics influencing the energy consumption of a public building and district with their subcategories: the general climate and the microclimatic conditions, including topography, wind exposure, and heat island effect. The district characteristics are categorized with morphology and density. The building's most influential characteristics relate to their orientation, building geometry, construction, and building services. The implementation of retrofitting projects are often interrupted, delayed, or postponed due to legal constraints, national or European regulations. Therefore, A2PBEER includes the different types and levels of legislative decisions currently available at the European Union, national, and city, district, or building levels. The aim of the stakeholder analysis is to identify all stakeholders who influence the energy demand in a public building or district, with their degree of influence, and to investigate their interests. The methodology is based on best practice methods tailored to public retrofitting projects. Influence can be described as the stakeholder's powers over the project, where a stakeholder with high influence can control key decisions. Stakeholders may have a high level of power if they have legislative power, political influence, or are financially strong, and important customers are led by influential spokespeople. Interests could be derived from stakeholders' needs and engagement relating to the proposed project or policy. Some examples can be reducing energy bills, which would be interest to building owners as well as building users. Improve indoor comfort could affect building users. Building owners would be especially interested in improving building maintenance, or building owners, users, architects would be interested in aesthetic requirements. The simple matrix helps us to understand the key stakeholders' influence and interest on the running and use of the building or the district. The level of power and interest are assessed on a scale from 1 to 5. The key players with high power and high interest should be actively engaged throughout the project, as they are critical for the success of the project. To meet their needs, high power but low interest, and show consideration, low power but high interest stakeholder groups should be kept informed, as they can act as supporters of the project either by their power or by their engagement. The least important, low power and low interest groups should be informed via regular general communication with a goal to increase their interest in the project. The technological recommendations of A2PBEER build on the initial step of the building or district assessment and the established priority list assessing the needs in the particular project. The gap analysis compares the actual state of the building with the predefined benchmark value via determines key performance indicators, identifying the hotspots where the intervention is necessary. Simultaneously, the best available technique, BAT analysis, identifying the gaps, is also carried out. This gives a result from collating the current technical status of the building district and the available technologies list, highlighting, as the name suggests, the best ones from the perspective of the particular project. Sequentially, the technical packages are selected later based on the evaluation of synergies and the retrofit strategy. The gap analysis and the energy strategies definition outline the intervention areas, which, combined with the BAT, results in the so-called technology priority list. This extensive list requires further filtering by constraints analysis applicable to the project. Some technologies are eliminated from the list based on the compliance with the features of the specific building district location or with particular building requirements. Operating conditions and climate are considered as two main constraints aspects in the tool. Further filtering determines the preliminary shortlist of possible technologies. Energy strategies are investigated to determine the cooling and heating loads and strategies to reduce these. The reduction of artificial lighting is also a major factor in public buildings, with the aim to increase daylighting use. How the energy is used within the building is investigated, taking into consideration the financial constraints as well. Technology recommendations are provided which outline the benefits of each technology retrofit with the aim to provide the best practice retrofitting approach for the building. Categories of technological solutions and systems build on the developed overview of over 200 available energy-efficient solutions and systems for buildings and districts retrofitting under low energy use criteria. Solutions and systems are classified in 5 main categories, representing the most relevant intervention areas, as these contain a total of 17 technologies as subcategories. The main categories also represent a recommended sequence. First, minimize the envelope heating and cooling loads with the design of the envelopes and interiors of the building. Then, analyze all of the daylighting opportunities, including in lighting categories. These have a double benefit. Energy usage is reduced, and a smaller size heating, ventilation, air conditioning system is needed. Then comes the selection of the HVAC to ensure systems energy efficiency under improved service category. This is followed by elevators specifications and continued by determining the renewable energy solutions, their production and storage. Finally, it is important to consider the synergies amongst different intervention areas at district scale. There are several potential technological combinations for retrofitting under low energy criteria, taking into consideration each building's circumstances such as climate, building use, cost, and technological performance. Therefore, it is not just the energy targets and cost reductions that should be considered, but it is also necessary to present the main stakeholders' requisites from the early stages of the design decision-making process. According to the public building stakeholder analysis carried out within the A2PBEER project, the major concerns of the key players are related to technology feasibilities, costs, operational and legal requirements. Therefore, A2PBEER recommends to perform a SWOT analysis in order to identify the best suited intervention package. A SWOT analysis is a structured planning method to evaluate the intervention package from different aspects. The analysis includes strength, the main advantages of the technological package over the other, weaknesses, the main disadvantages of the technological package over the others, opportunities, the possibilities that the project could exploit to its advantage, and threats, issues that may cause problems for the project. After the introduction of the methodological framework, let's see how the web application works. The application can be accessed from A2PBEER main site or directly at retrofit.atbeer.eu. The welcome page displays the process of the web-based A2PBEER support guide for public building district retrofitting toolkit. The website provides the key information in a clear, concise, and easily understandable way. To access the tool, first you have to register. You need to complete the information by selecting a username and a current email. An automatic confirmation will be sent to the chosen email address along with the password. Then you can log in to start using the A2PBEER retrofitting application. There are 6 sections which show on the home page, but there are also displayed on the left-hand side of all subpages. These are district and building, national standards, stakeholder analysis, technology recommendations, self-assessment, and best practices. Start the step-by-step process by district and building and continue until all sections are completed. On each page, on the right top corner, there is a Help button, which helps you with the list of instructions on using the web tool in that particular section. Once you are logged in, the page for the district and building section is displayed. The initial step after registration is to add a new building. You have to fill in a survey by examining the building or district characteristics. On completing the survey, this information is automatically incorporated into the following sections to provide recommendations on best practice and energy-efficient solutions. As described before, A2PBEER have formulated a database from a range of buildings and districts by collecting information on their climate, district type, building characteristics, and other data. The survey's filtering criteria has been designed so that in-depth knowledge on the building or the district is not required, that non-expert users will also be able to complete the questions. Typical values have been assigned to each answer as part of the information collated from other works about public buildings. The energy demand from heating, cooling, ventilation, domestic hot water, and lighting are the estimated values and compared to a reference building for each building function. Each category related to the energy consumption of the building is provided with options, and the answers can be chosen from the drop-down menus in the web tool. The example on the slide highlights the characteristic of the microclimate, in this case a Nordic situation, where main consumptions relate to heating. For the topography, you have to determine whether the building or the district is located on a flatland, a valley, a southern slope, or it is in a peak position. It is required to give information on all the themes. Also, the survey uses restricted options rather than open answers. If the answers do not offer the exact description of your project, you should always select the most appropriate or closest answer. In the case of each parameter, a short description is given to help the selection. The energy use is calculated based on a parameter sensitivity analysis. Therefore, it is only an estimate, and only the relative significance of the different energy usage is displayed. For example, if the tool estimates that the heating energy demand is responsible for the largest share of the energy usage, the tool recommends that high priority should be given to technologies aimed at the reduction of the heating energy demand. The tool automatically includes some technologies and excludes others according to the selection of the owner. For example, if the building is fitted with single glazing, then glazing technologies will be recommended. But if the building already has triple glazed modern windows, then these technologies will be excluded from the list of recommendations. Upon completion, Update button should be pressed. The results will be displayed in a drop-down menu form where each recommended component, like heating or electricity, can be selected. By selecting them, a list of recommended technological solutions for the displayed category will be downloaded in a PDF file. District and Building section also allows you, besides adding a new building, to edit a building and refine the characteristics, or delete any of it if you have entered the building in error or you do not need it anymore. This page also allows you to download and print out the results about any or all of the buildings you have entered, and you can choose to include one or more characteristics sections like building characteristics, national standards, stakeholder analysis, technologies, and practice. Step 2 should be used to compare your building against the national standards in your country. The first item shown in the chart is the thermal versus electricity energy use in your building. This is calculated based on your input when you entered this building. There are a number of fields on this page where you can enter your energy use for your building or district, and this is compared against the national standard to give you an indication of the performance of your building. The stakeholder analysis is prepared as a self-assessment. You enter stakeholders' profiles one by one in an easy and straightforward interface. Further stakeholders can be added by clicking the Add Stakeholder tab. After completing the stakeholder profiles, results are generated in a matrix format, which is a visual representation of the importance of the stakeholders. There is an option to print out the user matrix with an extra button on the right upper corner, offering different output formats: non-vector and vector image, or PDF. Based on selected technologies and other parameters, the guide produces a technologies shortlist, tailored to filter the solutions for your building characteristics. This can be the basis of the final intervention package and energy strategy for your project. The technologies list is arranged into an expandable menu in the building service categories: heating, cooling, ventilation, lighting, domestic hot water, and electricity. In step 5, you have to complete a SWOT assessment of the possible retrofit intervention package based on the work completed in steps 1 to 4. A user-friendly, straightforward matrix layout is provided, with information boxes next to each component of the SWOT. A list of criteria are suggested in the scroll-down columns next to each category. As you may want to evaluate different intervention packages, further SWOTs can be added. These can all be downloaded by clicking the Download SWOTs tab at the end. Step 6 is the final step. It gathers various examples of public buildings in Europe which have been retrofitted to a high level of energy efficiency and can be considered as best practice. The criteria included low renovation costs, a wide improvement in energy use, moving from more than 300 to less than 50 kWh per square meter per year, and lower CO2 annual emissions. Please try and test the A2PBEER support guide toolkit so we can discuss opinions and get feedback from you. Also, please do not forget to fill in and return the feedback sheet. We would appreciate to hear your opinion and thoughts for refining the methodology and the tool to serve public building and district energy efficient retrofit decisions. Thank you for your kind attention.